Good afternoon, everybody. Thank you so much for joining us. We have a handful of people that are still popping on, so while we wait, I will go ahead and point you down to the bottom of the screen where your Q&A box is. If you have any questions at any point in time during this webinar, please feel free to go ahead and put those in the Q&A box, and we'll make sure to get to them as soon as we can. There's 3 different presenters today who all have introduced themselves in just 1 second. Each one of them will be taking small pauses throughout the presentation to take your questions, but please do not hesitate to go ahead and shoot those over as you think of them. All right. Let's go ahead and get started. First, I would like to introduce you to the 3 panelists that will be presenting to you guys today. And we'll just go ahead and start with the first one and make our way down. So Dale, would you like to introduce yourself?
Yeah, if you can hear me. Hi, everybody. My name is Dale Kerner. I'm the permitting manager with Midas Gold, Idaho. I've been with Midas Gold for about 3.5 years now, and this project, of course, predates me by several years, but I've been here for some of the most exciting ones. So we're very glad you joined us today. This is a topic I think does and should get a lot of attention, and we've got a great presentation for you today to pass along some good information from folks who are very much in the know about these topics. So we hope you enjoy and get some good factual information today. Thanks.
Yeah, my name is Austin Zinzer. I'm the Senior Resource Geologist for Midas Gold. Been working on this project for almost 10 years at this point, from exploration through development here. And particularly, I've been working with some of our consultants on geochemical characterization and how that information gets applied towards modeling water quality associated with the project.
Hi there, I'm Doug Durbin. I'm a chief scientist with Brown and Caldwell. We're a consultant that's assisting Midas Gold with this project, and I specifically have been focused on the surface water quality and some of the groundwater quality issues, and also on pursuing the Idaho Surface Water Discharge Permit, or the NPDES, or sometimes IPDES permit, depending on whose acronym you'd like to listen to. So I'll be talking later on about the water treatment process that is part of that permitting effort.
Wonderful, thank you guys. We also have a few other folks on as panelists that will be here to help answer any questions that you might have. Paul Leonard, Michael Boger, and Mackenzie Lyon. So real quick, while before we get started, just one more reminder, if you guys have any questions at all, go to the bottom of your screen, click on the Q&A box, and go ahead and type that question in. We'll get to those questions as soon as we can and throughout the webinar. With that, Dale, go ahead and take it away. You're on mute, Dale.
Just want to verify you guys are seeing the screen.
Yes, we are. Thank you.
Okay. All right. Very good. Okay, everybody. Thank you for joining us today. Again, we've got a lot of ground to cover here, but it's a lot of very interesting and informative ground. And I just want to cue things up here a little bit on the front end here before I hand it off to Austin and Doug, who are very definitely our experts on these topics. But in putting this presentation together, these are some of the questions that I've seen surface from people. They're questions that I have about our project, and they're questions that I hope you feel are sufficiently covered today. Of course, we have the Q&A function, so you can supplement these questions with others that you may have. But briefly, we're going to talk today about existing water quality at Stibnite. Certainly, there are water quality impacts at Stibnite. They have multiple sources, both legacy materials and natural mineralization. So we'll talk a little bit about how what the water quality is and what the sources are. And that speaks to number 2, what are those causes? And Austin will give us some information on that. We've also done a lot of work, both the water monitoring that we've done and all the modeling and all the models that we've created using all the information about the site, and we're able to, you know, understand how the Stibnite Gold project will potentially impact water quality. So we've got a pretty good idea of what those potential impacts are, and we'll talk today also about number 4, what will be done to mitigate those impacts to water quality. You know, we'll speak today to certain best practices with regard to during construction operations and during reclamation, how we can minimize impacts to water quality, and in the cases where those impacts are unavoidable, how we can treat that water to ensure that the water that we are discharging meets appropriate standards. So we will speak about different phases of the mine life today. We'll talk about construction, operation, and reclamation phases, and how our water management changes over the course of those phases. Because of the footprint of the mine changes, we have to adjust to some degree how we're managing that water. We'll go over those details. Then finally, you know, what will be the net benefit of the Stibnite Gold project with regard to water quality? Of course, we want when we walk away from this site for water quality to be improved in the long term over the current impacts that are out there today. So again, please supplement these questions with questions of your own today as we're moving through our agenda. I'm going to give you a very brief intro to the project. Hopefully you've been on one of our many webinars in the past, and I'll just take a couple slides to kind of bring us back to the site and the layout and some very general information, and then I'll pass it off to Austin, and he will talk about surface and groundwater quality. A lot of the years and years of monitoring we've done out at the site. Now we've taken all these data with regard to the surface and groundwater quality and the rocks that will be disturbing as part of the mining operation, and all the geochemical characterization that's gone into those efforts to understand what the potential impacts will be moving forward. Then we'll move into water management and water treatment, and we'll pass it off to Doug Durbin with Brown and Caldwell for that discussion. And we'll get an understanding of what we want to do, what we can do during all these phases of the project to ensure that we're protecting water quality and improving water quality. And Doug will dive into a little bit more of the details about how we came to the treatment technology that we will utilize at the site when we do have to treat water, again, during multiple phases, and then how those will be implemented. And we do want to leave plenty of time for discussion and questions, and we'll take a couple breaks during the presentation today to allow for that as well. So, the Stibnite Gold project. I think, again, hopefully most of you are familiar with where our project is located. It's in a fairly remote site in Eastern Valley County, east of McCall and east-northeast of Cascade. So here's a map just kind of illustrating where it's at. It takes about, I don't know, 4.5, maybe 5 hours to get there from Boise, and just a couple hours from Cascade or McCall. And it's on some of our other webinars, we've talked about access to the site and how important that is, and how we, how we've evaluated how to get there safely and to minimize their environmental impacts in doing so. So here's a map just to orient us all as to where we're at. And then, of course, the Stibnite Gold Project Plan of Restoration and Operations. Now, this came out in September of 2016, which seems like a long time ago, but the last 4 years have really flown by. But Austin mentioned he's been with the company for I think 10 years. There's a lot of preparation that went into into putting this document together. Years of baseline studies, years of monitoring for surface and groundwater and other media that are out at the site. So this was a very sound plan, a very good document that was put up in September of 2016 as our proposed action. So we, of course, see a lot of benefits to our plan for cleaning up legacy impacts out at the site as part of the mining operation, and also, conducting restoration to some of the functions and of these, ecosystems out at the site. One of the biggest one being reconnecting you know, anadromous fish travel across the backfilled yellow pine pit, which you see in the photo there. And the August 14th, the draft EIS came out for the pro, and we certainly want to encourage you to comment on that document during the public comment period. So today we'll be talking a lot about the site. This is a figure right out of the pro. That is the layout of the mine site, and again, hopefully you're somewhat familiar with the hydrology of the site. But you know, one of the things I like to just point out on this figure is the fact that, you know, the east fork of the south fork of the Salmon River, you know, which flows kind of through the central portion of the site, the tributaries coming into the east fork of the south fork and the east forks of the south fork itself, everything's flowing northward. So that, you know, in general, flowing northward, including the groundwater flow. So as we talk about this, as we talk about surface water and groundwater today, just bear that in mind, that that's kind of the overall flow of surface and groundwaters across the site. You can see our main features here, including the you know, the Yellow Pine Pit. We do have 3 open pits: the Yellow Pine Pit, the West End Pit, and then the Hanger Flats Pit. And you'll see other features on here as well: the development rock storage facilities, both West End and Fiddle, and then the tailings storage facility. And of course, the worker housing facility down here on the southeast end of the site. So just giving you a little overview here. Again, hopefully you've seen this probably numerous times, but just a little refresher. And then I will wrap up my discussion today with, you know, I've spoken to this a little bit already, but where we're at in our process. If you look at this diagram in the upper left corner, it moves clockwise around in its progression. The submittal of the pro in September of 2016, and there's been a lot of activity between 2016 and today to, you know, get the agencies, interdisciplinary teams put together, the third-party EIS contractor, getting all that scoping done, and working on the alternatives development for the alternatives that are included in the draft EIS. If you're familiar with it, you'll know that there are 4 action alternatives and the 5th no action alternative. So hopefully you've had a look at that document and you've been able to provide a comment to the lead agency, the Forest Service, with your views on that document. And at present, that comment period is ending in October of 2020, and then we'll move on with continuing to the final EIS and the draft record of decision, probably around, you know, Q2 of 2021, and then finally a ROD, we hope, in late 2021. So that kind of brings us back to the now, and we're going to kind of push all that permitting and stuff aside, at least in the NEPA sense, and focus on the topics at hand today. And we are going to start with water quality. So Austin, with that, I will hand it off to you, and I will mute myself.
Yeah, great. Hopefully everybody can hear me. I'm going to be talking about water quality today. I'm going to be talking about existing water quality on site. What are some of the major legacy mining features that are impacting current water quality? And then we'll probably break for questions before I talk a little bit about the geochemical characterization program and how Midas has collected data to use for predictive modeling. So Midas has been collecting baseline water quality data since 2012. And the monitoring program consists of 32 surface water stations, primarily on the East Fork, South Fork, which on the map is the main drainage that runs through the center of the project area. And then also on Meadow Creek, which is the large drainage to the southwest on the map. In addition to the surface water, there's data collected from 23 natural seeps, adit seeps, ponds. We have an extensive bedrock and alluvial monitoring well system from which we collect baseline water quality information. And the data has generally been collected quarterly more recently, but it was collected monthly for the first couple of years of the project. And this has really helped us understand seasonal variations in water quality throughout the site. The water quality samples are analyzed for a suite of metals, cations. We take field measurements. And this is quite a bit of work, and I just want to applaud all of the personnel who are involved in this program and collecting the data and ensuring data integrity. So generally, throughout the site, we see elevated arsenic and antimony as the key constituents of concern that are elevated in surface water and groundwater. These constituents tend to be elevated downstream of a lot of the legacy mining impacts on site. And these legacy features are a principal source of metals entering surface water, draining from the former mining areas. However, there's also a lot of areas of the site that haven't been mined historically, and these areas also show elevated metal concentrations. And this is sort of consistent with presence of naturally occurring mineralization and water quality impacts associated with these natural sources on site. Throughout the site, over the entire last, sort of 60 years of records, there's really been no evidence for any sort of acid rock drainage or acid generation on site. And this is just a function of the site's unique geology, specifically presence of a lot of carbonate rocks in the area. That said, we do have impacts from arsenic and antimony. And these generally show a inverse relationship with discharge, where during peak spring flows, when the water has the highest flows, we see the lowest metal concentrations, and the highest concentrations when the flows are low. So a couple of the different sort of types of legacy mining features that impact water quality are both those associated with underground mining, such as tunnels and adits. Here's a picture of the DMEA adit seep on site. And then the other large features are more of surface mining features, such as soda. Can we go to the next slide, please? Soda is the spent ore disposal area. This is a large area of spent heap leach ore from 1970s and 1980s operators that was placed directly on top of tailings from the 1940s and 1950s operations, which were deposited in Meadow Creek by the Bradley Mining Company. This area, the soda and the Bradley tailings, is one of the principal sources of metal on site entering streams. So we're going to look at water quality today and how it changes as we move from upstream to downstream. So we're going to be looking at a series of plots that have water quality data starting up in Meadow Creek, which is down in the southwestern part of the project area. And then we're going to move past the confluence with the East Fork, South Fork, and then down past the Yellow Pine Pit. So just some photos. The photo in the upper left is a photo of the Yellow Pine Pit as it currently exists today. This is one of the major sources of metal entering water, or this and the Bradley dumps, which are nearby. And then also down in the lower left is a picture of Upper Meadow Creek, and you could see where the soda facility is with the Bradley tailings beneath it, and then the site of the former mill and smelter complex, as well as the Hecla heap leach. These are all features from legacy mining operations that are believed to impact water quality today. This line chart here shows the range of arsenic concentrations as measured in surface area in the East Fork, South Fork, and in Meadow Creek, the primary tributary. And as we move from left to right, or from upstream to downstream, you can see that that metal concentrations are consistently elevated above the Idaho Human Health Criteria, which is the lower red dashed line. This is the recommended limit of 10 micrograms per liter of arsenic to make it safe for human consumption. So only during the high spring flows do we see concentrations below that criteria. And then as we move downstream, the concentrations increase in the reach below the Yellow Pine Pit, where the Bradley dumps are. And then they decrease again as Sugar Creek basically dilutes water quality or dilutes water and improves water quality in the East Fork. Similar data for antimony, where you could see that antimony generally steadily increases from concentrations approximately around the human health criteria of 5.2 micrograms, and steadily increases as we move downstream before we see dilution associated with Sugar Creek entering the East Fork of the South Fork. Mercury is a little bit different. Mercury is not elevated in surface water on site above the criteria of 12 nanograms per liter. But we do see a spike in mercury when Sugar Creek enters the East Fork downstream of the project area. And Sugar Creek, for those of you who are not familiar, drains the Cinnabar Mining District, which was a historic mercury mining district operated in the 1950s. So this is leads to exceedances throughout some of the year in terms of mercury. So I've talked a little bit about some of the legacy mining sources of metal in surface water. But a lot of I think it's important to understand that a lot of the metal concentrations in surface water in the area are potentially attributed to natural background mineralization. So this map here, this just shows the distribution of arsenic in soils. Arsenic is a metalloid that's commonly associated with gold mineralization. Of course, there's a lot of gold in stibnite, the stibnite district. There's also a lot of arsenic up here. But this map just shows the general distribution of naturally occurring arsenic in soils, and this reflects underlying naturally mineralized areas in the mining district. And generally, where we see mineralization in an area, streams that drain those areas also tend to have elevated arsenic and antimony concentrations. Next slide, please. So this is some data that we compiled from a report that was actually prepared for IDEQ back in 2000 when they were called the Stibnite Area Characterization Report. This was associated with some of the cleanup activities that took place around that time. But it just shows estimated ranges of natural background concentrations of arsenic and antimony in groundwater on the left side of the chart, and then also in mineralized areas on the right side of the chart. You can see that the concentrations basically are thought to consistently exceed the various water quality criteria, including the human health criteria and sometimes the human health criteria for recreation. So perhaps we should break and see if there's any questions so far before we talk about the geochemical characterization program.
Sure. Thank you, Austin. First question that came in is, are the values that you were discussing individual samples or aggregated average values?
The plots showing the statistical range, those are based on aggregated average values over throughout the period of the baseline monitoring program, which is basically 8 years of data at this point.
And Austin, can you explain the different colors for these different lines, like the?
Yeah, sure. So basically the minimum is the lowermost line, and that's shown in blue. The green line is the 50th percentile or the median concentration. And then it also shows the upper quartile, the 75th percentile, and then the maximum value. Generally, it's difficult to look at average values because of the seasonal fluctuations in water quality associated with high versus low flow periods.
So to that topic, then, if we're looking at these 4 different lines, would the minimum values at the bottom would be during highest flow periods or lowest flow periods?
That's correct. So the lowest concentrations of metals, at least for arsenic and antimony, occur during periods of high flow or high discharge, typically in June and March. Sorry, May and June. Versus the higher concentrations for arsenic and antimony tend to occur during base flow when there hasn't been a lot of precipitation, so in August or early September generally. Mercury is a little bit different. Mercury is primarily transported as particulates, so we actually see highest mercury concentrations during high flow periods when there's a lot of water moving and it can move a lot of sediment.
Thanks, Austin. One more question before we move on. How challenging have you found it to convince some people that there are naturally occurring metals and that they may be fearful of?
Yeah, it's a great question. I think it's, I think a lot of people, associate arsenic with mining activities rather than associating this metal with natural geological processes. And I think it's just challenging to explain these concepts to people because a lot of people don't have a strong geological background and aren't familiar with which elements are naturally occurring in Earth system processes, such as those that form mineralized deposits.
Great, thanks. We can move on.
All right, so we're gonna switch gears here and just talk about the geochemical characterization program. We jump into the next slide here. But basically, this is an ongoing project. It was started in 2011, actually, when Midas initiated its exploration drilling program to basically characterize the different geological materials that occur on site and were potentially going to be mined in the Stibnite Gold Project, and really understand how these behave from a geochemical perspective. So this program entailed basically collection of a large number of drill core samples and auger samples of both development rock and legacy materials that are present on site, in addition to some of the samples that are going to be developed as part of the gold processing circuit. The sample characterization consisted of basically understanding the chemistry and mineralogy of the samples, doing some short-term leaching procedures to understand what sort of constituents might be released from the samples, acid-basic counting to understand the potential for the samples to cause acid rock drainage, and determine basically the neutralization potential of these samples. And then a suite of long-term humidity cell tests, which ran for years to understand the long-term metal release rates of the different geological materials to be mined in the Stibnite Gold Project. And this picture here has some of the, there's the picture again on the next slide. This picture has an example of those humidity cells in a lab in Reno, where they lived for many years. So this is actually some of the data from the humidity test cell program, and what this graph is showing is pH on the vertical axis and time in weeks on the x-axis. So you can see that we ran these samples out. Each line on this graph represents one of the different humidity cells that were tested for a number of weeks, and a lot of them were tested for 140 weeks, which is an extremely long time for this type of test work. A typical duration is only 40 weeks. But as you can see from the pH measurements here, they all basically remained in the circumneutral territory with pHs generally above 7 throughout the duration of the test. So this is really good evidence that we don't have materials on site that we believe are going to lead to any sort of acid rock drainage issues. And this is, consistent with the behavior of some of the legacy mining materials on site that were mined and have been sitting out and weathering for the last 60 years as well. This graph shows basically similar information, but it's a bit more complicated. So the axes on this are neutralizing potential ratio on the x-axis and net neutralization potential on the vertical axis. But the take-home point here is that the samples that fall in the green box have a high acid buffering capacity owing to a higher carbonate content or carbonate mineral content. So these are samples that are termed non-potentially acid generating. Samples that fall in the orange box are potentially acid generating because they don't have sufficient carbonate buffering capacity to neutralize acid that could potentially be formed from sulfide dissolution. However, what I want to point out is that all of the samples that are colored red on this plot within the orange box, those are actually our ore grade materials. So really what this plot is showing is that of all the samples we tested, the only ones that, vast majority of the samples that are considered potentially acid generating are also actually our ore materials. So in the stibnite gold mining plan, the ore grade materials are going to get processed through the plant, which will naturally basically oxidize them and make them incapable of generating acid. And that the vast majority of samples that we've tested in the geochemical characterization program are not anticipated to be acid generating. So despite lack of acid rock drainage potential on site, we do think that some of our samples are going to potentially release arsenic and antimony under circumneutral weathering processes, where these metals are released without acid rock drainage. And then there's also potential for release of some other constituents, aluminum, manganese, minor selenium, and sulfate associated with some of the samples. And these results, of course, are generally consistent with what we see downstream of some of the legacy mining facilities on site already. I'm wondering if this slide has some animations built into it. There we go. Yeah. So, so next, I'm just going to touch briefly on the site-wide water chemistry model, which is the predictive model, which basically takes all of the geochemical characterization data that I was just talking about, and then uses this to build predictions of what water quality is going to look like associated with the proposed action. And this utilizes data from these other environmental models that have been built in support of permitting, including the site-wide water balance, the stream and pit lake temperature model, and the hydrogeologic model. So just a quick summary of what the results from the site-wide water chemistry model are. But basically that, the impacts from the project combined with a lot of the restoration activities are predicted to lead to a net improvement in surface water quality. So this chart here shows the results of the site-wide water chemistry model for some of the various alternatives being considered under NEPA throughout the post-closure period. And you can see time down there on the x-axis going from post-closure year 1 all the way up to year 100. So we're thinking really long-term with these. But basically you can see that under alternative 2, that squiggly purple line there, we're basically anticipating a net improvement in surface water quality on the order of approximately 30% decrease in arsenic and antimony concentrations over the long-term period. The current concentrations are shown by the horizontal green lines on the plot, which show the minimum, the maximum, and the average. And this is at a monitoring location that's all the way downstream of site. And this improvement in water quality is basically, the result of removal of legacy mining materials and placing them in places where they won't interact with surface water and precipitation. Of course, restoration activities and surface water diversions to divert surface water around existing mining facilities. So the predictive modeling, it really just allows for a way to compare some of the alternatives that are being considered, and also to identify potential areas for project improvements. One of the areas identified out of this work was water treatment and water management, which is what Doug is going to be talking about. And I just want to point out that these results don't apply any water treatment or water management. So we thought that we could build upon this and improve the project further through those activities, which is what Doug's going to be talking about next. I think that concludes my section, so we can open it up for questions.
Thank you, Austin. We do have one that just came in. Is there any mercury occurring in the soils or rock in the proposed mining area of stibnite?
There is some naturally occurring mercury in the mineral deposits of that we're looking at mining under the Stibnite Gold Project. It's very low concentration, and we've been measuring it in and trying to characterize it as part of the geochemical characterization program. But at this point, we don't anticipate the mercury release being an issue on site. The majority of mercury, just like the majority of arsenic and antimony, are actually going to be processed through the mill site, and that facility will be equipped with mercury scrubbing systems to remove any potential mercury release out of the flumes coming out of the processing facility.
Hey, this is Dale. If I could just supplement that with a brief digression into air quality. You know, mercury is also considered in ore processing and the potential emissions that come out of that circuit. You know, Austin mentioned these collection procedures for gathering that mercury. Any mercury that does make it past those safeguards is minimal, and if you want to see that quantified, you can see that in the draft EIS. But you know, it's the deposition of mercury from those emissions is very minimal.
Thanks, Austin. Thanks, Dale. So earlier in the presentation, Dale mentioned that there's 5 alternatives in the draft EIS that is out. Somebody had a question on what alternative would be the best to lower the current levels of arsenic and antimony impacts in the water. That slide that you just showed, I read that as being alternative 2. Am I correct in that thinking?
Yeah, that's correct. We think that alternative 2 is the you know, our preferred alternative as a company. We think that the primary reason is because it's going to have the largest benefit on water quality on site.
Great. And does this graph right here include water treatment?
It does not. Doug will be presenting an updated series of plots that show the results of alternative 2 with and without water treatment later in the presentation. I will point out though that alternative 3, as you can see on the plot, has the largest exceedances of water quality relative to the sort of existing conditions, and this is the result of not relocating the Bradley tailings from Upper Meadow Creek. So those mining features in alternative 3 will continue to release metals and metalloids into the surface water.
Wonderful. Thank you, Austin. I think we're good to proceed.
Okay. I'm going to talk about overall water management and treatment. I'm going to do it in 2 pieces in that order. So let's jump to the next slide and start talking about management. The overall reason to manage water, which does include the idea of treatment, is to make sure that we don't have undesirable impacts on the environment. And as the first bullet here indicates, the primary goal is to make sure that we comply with the Clean Water Act. As somebody who has done this kind of work for almost 30 years, I don't see a pathway to approval for a project like this if you can't say that you're going to comply with the Clean Water Act. So that's kind of the gold star target that we're aiming for. The notion behind our water quality management is that we will manage and treat all the mine impacted water that has to go back into the surface water environment. There's going to be provisions made for treatment that will start during construction and that will continue then all the way through the operations phase and the reclamation and the post-closure phase for a time period that will ensure that the facility is brought back to acceptable conditions before that treatment would cease. The management plan was developed is in the draft EIS in association with alternative 2, but it was developed specifically to be adaptable so that it could apply to any of those alternatives or also to any modifications that might be made to the mine plan after the mining starts, which is a pretty common thing for mine operations to see things get tweaked as we learn more about it. It's important to know also that the water quality management plan was reviewed by EPA and by a bunch of other agencies, and we responded to all of their questions and comments before we finalized that plan. So it's not a unilateral plan, it's a plan that had broad exposure and responded to interests of those parties. Okay. The primary objectives of the water management plan is to protect the surface water and groundwater during operations and then also during the long term. So that is after closure, after reclamation, make sure that the things don't turn around on down the road. And then obviously to provide through those improvements for some kind of mitigation for surface water temperature issues that already exist at the site, and of course across a lot of Idaho, unfortunately, with respect to water temperature, because water temperature is very important for the protection of some of the salmonid fisheries. Okay, so this is a sort of a big picture view of how we like to think of all environmental management, but specifically here with water management. The first thing we look for is how can we avoid having any opportunity to degrade water? What can we do to keep the clean water clean? And I'll talk about that with some graphics here in a minute. So we avoid making the clean water dirty. Next is, if we have water that's going to impact some of our facilities, some of our operations, what can we do to minimize the opportunity of that picking up contaminants or constituents? And then finally, if we have water that does get dirty, what do we do to mitigate that? How do we prevent that dirty water from going into the streams and downstream and affecting something else? And then as the cloud up there in the corner shows, we do want to have a plan that's adaptive so that the things we learn about or the things that might change environmentally through the process can be pulled into our planning. We don't have a rigid plan that can't ever change. We want a plan that gets better through time. So here's a graphic of kind of an oblique view of the site that shows some of the water management concepts. There's a lot on here going on. I don't have a pointer, unfortunately. If you start at the left-hand side of the screen, you can see that is the tailings storage facility that's proposed, and then just downstream from that is the development rock storage facility in the Hanger Flats area. And you can see little light blue lines that are routed around the edges of that. And they're in several other places on here as well. Those light blue lines are the rerouting of existing streams so that we don't have to dam up the streams. We don't prevent the water from getting down the mountain, but we also don't let that clean water that's coming off of the hillsides run onto the TSF or the Hanger Flats DRSF. The clean water runs into those little blue ribbons and stays clean as it goes down the hill into the existing streams. So those are a big part of keeping the clean water clean. In the middle of the facility, you see a label for the proposed water treatment plant. We call it the WTP. That's the place where the dirty water would be treated if we need to release that water back to the environment. And that ensures that we don't have a negative impact on water quality with the water that does happen to pick up some contaminants on the site. And as you can see further downstream, we have more reroutes of things that go around the various facilities. I'll talk a little bit more about those as we go on. Next slide. So here's a kind of a zoom in, makes it much easier to see those little blues of the rerouted streams. Another thing that's happening at the tailings storage facility and the DRSF is underdrains. An underdrain is exactly what it says. It drains clean water underneath a facility to make sure that it doesn't get contaminated with what's above it. That TSF will have a high-tech, highly engineered liner underneath it so that the material that goes into it will be isolated from the water that's underneath it. And that underdrain makes sure that the groundwater continues to move down that valley and move on off the site without being contaminated by what's in the TSF. Okay. This is during the construction period, and we obviously are thinking about ways to make sure that we have very little risk of water quality degradation during construction. One of the first things that happens is to pick up some of the old contaminated materials. You can see the word soda in one of those labels there. That's the spent ore disposal area from some of the legacy mine works. That'll be picked up, and that is a current source of contamination, as Austin talked about, for both antimony and arsenic, and that will be moved away so that it is no longer a source of contamination to Meadow Creek. The Hecla heap is another legacy pile of material that will be stripped away in preparation for mining, but also as a means of reducing a source of poor water quality. You can see that Meadow Creek, the little green squiggle there, Meadow Creek will be routed away from the Hanger Flats pit. That will keep that water from running into the pit, and also then we'll put it into a location that is away from that, mine facility. And then there are further enhancements that are happening. This talks about a Meadow Creek enhancement, but there are various habitat enhancements that are happening that are not necessarily part of our water quality concerns, but are part of habitat and fisheries improvements. Okay. During the operations period, which is scheduled to last for somewhere between 12 and 14 years, there will be active management of water, and that means many different things. One of the most important ones is in the lower left-hand corner there. You see the label that says recycle process water. One of the very best things that this plan does is once the water is part of the process, that process water is not released back to the environment. It continues to be used and reused and reused, and some of it evaporates, so it does disappear into the atmosphere, just the water part, not the contaminants. But recycling that water means that you don't put dirty water into the environment, and you don't have to use new water all the time. You're reusing some of the water that you've already used. You can see the label that says pump dewatering water. For use or route to ribs. There will be dewatering associated with the mine pits to make sure that the mine pits stay dry, and that water will become part of the process as well. So that water will end up being used and reused and reused. And then you can see the third label there talking about contact water in ponds. We have a series of ponds around the site that will be used to collect and store water that has come in contact with some of the mine facilities. So in other words, when snow melts and runs into a mine pit, that water isn't just pumped out into the stream. That water is pumped out, put into a contact water pond. It's either used at the processing facility to help extract the ore, or it is treated and released if there is excess water. So these are some of the things that go on during operations, and there are many nuances that are even more detailed, but this is a big picture view of some of those active water management operations, okay? During reclamation, many different things happen then. During construction, there's actually a tunnel that will reroute the flow of the East Fork, South Fork, Salmon River around the Yellow Pine Pit. That will be active during the entire operations period, but after the mine closure has occurred, you can see that green squiggle that runs across the top of the brown Yellow Pine Pit backfill. That's the restored channel of the East Fork, South Fork. So it's put back to configuration so that it flows on the surface. It is available as habitat for fish and other aquatic animals, and is back in more of a configuration like it was 100 years ago than like it has been for the past half century or so. Other creeks, the same thing happens. Many of them are slightly relocated, or the diversions that were put in place are moved back onto their more normal flow path. You can see that for the Phil DRSF. You can see that for part of the West End Creek. If we go to the next graphic, it's a little bit further upstream from this. Oh, I'm sorry, the next graphic. I guess we didn't include the next graphic. There's another one that shows a little further upstream, and the same things are happening there. Take my word for it. Okay. So let me pause there for a minute, and I've now talked about the water management, which in essence here was how do we keep water where we want it to be, hold water when we don't want to let it go, reuse water when we can. Any questions on that sort of holding and controlling of water?
We do have a few. The first one is, how will you prevent stream flow over the Yellow Pine Pit from going underground and collecting minerals?
Are we talking about, during the mine period, the tunnel that you see is the blue dotted line, the thick blue dotted line here, the tunnel will carry the flow of East Fork, South Fork around the Yellow Pine Pit. After Yellow Pine Pit has been mined out, it's going to be backfilled with some of the material that will come from the West End Pit until it basically is back to its historic grade or close to that. And at that point, a liner will be put across a portion of the surface of the yellow pine pit backfill. So if you can picture that you've got a hole in the ground and now you've filled it back up, and now you take a very wide, heavy duty plastic liner that is many times wider than the stream, you put that across that top, that surface, and you route the new stream across that. And that'll use clean fill, clean rock materials that are much more like what you would find in a natural portion of the stream. So you have basically built the new stream on top of a plastic liner that's buried underground. I hope that answered that question.
Thank you, Doug. Last one before we move on. Once cleaned up, picked up and cleaned up, where will the soda and other heap leach tailings be moved to?
The soda gets actually used as part of the embankment. You see on this graphic, it says TSF embankment construction started. A part of that embankment will be the soda material. So it'll be buried very deep, ultimately hundreds of feet beneath other materials. So it'll become isolated from exposure to rainfall, snow melt, and things like that. And that isolates that soda material compared to today, when every time it rains, water runs through and off of the soda and carries things like arsenic and antimony with it right down into the stream.
Wonderful. Thank you very much. I think we're ready to move on.
If I could just add one thing to that, Doug, then the underlying material, the Bradley tailings indicated here, which are also within the soda footprint, albeit underneath that spent ore, those Bradley tailings will be reprocessed at the plant, just as we would process, any other ore, and then those tailings will be placed into the tailings storage facility.
Great. Thank you, Dale.
Mm-hmm.
I think we're ready to move on to water treatment.
Okay, now let me talk about water treatment. And there's an important point to make before I even get to these riveting bullets, and that is that there's a lot of analysis that's gone on about the amount of water that will be available, what is in the environment, what falls as rain, what comes down as snow, when is it there, how is it different from one year to the next. Lots of models, lots of spreadsheet analysis have gone on with that, and also a deep analysis of what amount of water will be needed for the ore processing. And then the two of those are merged together, and what you get is a sort of a roadmap of when you have more water than you will be able to use at the mine. And when I say more water, I mean more water that has contacted a mine facility. In other words, water that's not necessarily clean enough to release. And the good news there is, as we tighten up those estimates, we find that there's not really going to be a huge amount of extra water. In other words, we're now managing our water so that most of what touches our disturbance, we end up using somehow. So the clean water stays clean, keeps going downstream for the fish and so forth. The dirty water is captured in ponds, or sometimes it's actually captured right there at the plant site, and it gets used in the mill or in the process, or even sometimes for uses like dust suppression on some of the roadways, which is also a very important thing. So the moral about water treatment is, how do you make it so that you treat a minimum amount that you need to treat, because you're using the rest of the water and preventing the need to even release back into the environment. So again, the water treatment plan is demonstrating that we are going to maintain compliance with the Clean Water Act. We would not have any discharge to surface waters that would exceed the state water quality criteria. And we know that the overall process is scaled to meet the needs of the EIS, and part of that is an active treatment process. Active treatment means that you are putting energy into it. It requires electricity, or to run pumps with a diesel generator, but you're moving water around actively, you're treating it actively, you're putting energy into the treatment. But then there are also opportunities that are well tested and documented for using passive treatment. And that is a low energy type of water treatment, things like wetlands or passive evaporation or infiltration, where you're not having to invest fossil fuels or electricity to get water, again, to meet the same endpoint criteria. You're just not having to invest energy into that under the passive approach. the idea is that overall, you have the ability to meet the Clean Water Act requirements, both during construction operations and also after mine closure. Okay. So an overview of the treatment plan is that, first of all, as I mentioned before, it could be adapted and scaled to any of the alternatives that are looked at in the draft EIS, or even new alternatives that may come up through the rest of the NEPA process. An important thing to keep in mind is that there's not even a proposal to treat and discharge any of the processed water or the tailing storage facility water during operations. That is, it would be a completely recycled system, and it wouldn't be until closure that there's a need to shrink down that amount of water and then treat and discharge water only as needed. The contact water ponds, as I mentioned, are largely needed because of the seasonal variability. During most of the year up there, there's not enough water that will be touching the mine facilities to even keep the mill, the ore processing facility going. So only because of the snow melt and the higher runoff during those periods that those storage ponds are really necessary. So that again means less amount of time when you have a water inventory that you have to think about treating, and less potential need to discharge that treated water. There will be a series of tests, both for the active treatment and for the passive treatment technologies. In other words, we don't just go out there and build a plant and say, okay, this will do. We actually, as the construction starts, we look at the actual water that's there at the facility and start running it through tests to confirm that the treatment processes and the scale that we're thinking about them at will be appropriate. And then we build exactly what is needed for the facility. That's a really important check, because while our engineers are really good at what they do, they know enough to know that you want to make sure you actually do a road test before you buy that car, so to speak. Part of the process that has already happened and will be revisited actually in part is to look at the various technologies. There isn't just a one-size-fits-all technology. And so this is a list of the principal technologies we evaluated. Each one was looked at in terms of the footprint it needed, the cost, the feasibility to remove certain parameters. But in each case, you can see that a result was determined as to whether or not a particular technology would be suitable for the anticipated water quality at the mine. And one of the things you see here is the two of them were thrown out. Adsorption was thrown out as being not feasible. Ion exchange columns were thrown out as not feasible. It's because there's simply not an appropriate way to incorporate those into the mine plan, but everything else has more or less applicability. You can see the second one on the list, iron coprecipitation. That one is seen as having the greatest applicability to this mine, and it's the one that is currently being considered as the primary treatment. But the other ones would be brought in and used at smaller scales as needed, which is a redundancy and kind of a custom fit to the overall treatment technology. Okay, so in terms of the next steps, you can see this this endless loop here. But you plan your water quality, your water treatment management plan. I just talked about the box that's to the right of that. You do your technology confirmation and your pilot tests. You evaluate the results. Then you do those tests again. Maybe you do a finer scale, higher resolution. You evaluate the tests again, and then you figure out what actual sizes and locations that you need for things, and you keep running through that loop until you have the plan that works for your mine. And as I said, adaptive management means that you might get 6 or 7 years into the plan and decide, hey, let's check another technology that just came out on the market that can do a better job or be more efficient, and you see if you might incorporate that in. So constantly looking for ways to improve what we're talking about. The overall water treatment program looked at not just the 3 parameters that Austin emphasized. You can see arsenic and antimony and mercury on here are in bold. Those are the parameters that have been identified in historic documents and agency studies and so forth. And so we know that those are of concern, but We also know there are other things that are typically found as possible contaminants or things that we have to be concerned about. pH, for example. Austin talked about acid generating potential. So you want to look at pH and think about the ramifications. Temperature, we know, is already an issue in many Idaho streams. So of course, we're looking at temperature. Some of these other things are on here because they've been found to be issues at other mines, or we know that there are federal criteria that must be applied to any gold mine simply as a matter of regulatory process. So we feel like that we are being very conservative. We are looking at a much longer list of things than we really feel like had the potential to cause a problem, because we want to be sure. So I'm not going to go through this line by line. I'm sure you're relieved, but this is simply to show that there are many different facets of treatment. That's the left-hand column, right? The treatment method, and the mine life overall goes from construction through operations, reclamation, post-closure, and then even beyond post-closure. And the moral of this graphic is that there are, in most cases, more than one treatment consideration that goes through that entire process, literally from 3 years before mining begins until as long as 40 years after mining is complete. So here, this is looking just at the location of kind of the treatment and discharge locations. And you can see there's a label that says outfall. The proposed outfall has not been absolutely determined down to the closest foot yet, but we have zeroed in on a section of the stream that seems like it meets the criteria. And so that would be somewhere along that stretch of the East Fork, South Fork, close to the ore processing facility. There would be a formal outfall there with extensive monitoring requirements and reporting provisions. And the treatment plant will be somewhere in the vicinity. Again, this is an approximation, but the wastewater treatment plant will be somewhere near the mill. And that's for several reasons. One is you already have a lot of materials and water coming toward the mill. And also that's where you tend to have access to power and personnel and things like that. So you can see that it's somewhere in that pink area. The other outfall that's down toward the right-hand side, I haven't really talked about this at all, but there will be a second outfall that's kind of a different variety. You can see it summarized in the left-hand column at the bottom, but basically it'll be a small-scale domestic wastewater treatment plant, not unlike what you would have for a small town, because there will be several hundred workers at a time using the worker housing facility. So there will be bathrooms and kitchens and cleaning and things like that. It's not a facility where we have to worry about things like arsenic, antimony, and mercury. It's one where we worry more about like oils and greases and soaps and things that might come from, like I said, showers, as well as the sanitary waste stream. And all of that will be taken care of through a very conventional process that essentially can be brought in and worked just the same way it would, like I said, for a small town or a small commercial facility. So here I'm going to talk, Austin foreshadowed this for me. I'm going to talk a little bit about some of the modeling. This is a map of the entire site, and if you look at the top of the map, where the cursor is circling there, there's a monitoring location known as YPSR4, and that happens to be downstream of nearly all of the Midas Gold proposed activities. In addition to being a monitoring location, it was also used in some of the water quality modeling. What that allows us to do is look at the existing or baseline conditions from the monitoring, as well as the projected or expected conditions after the modeling takes into account the mining process, and in our case here, the treatment. So let's look at a comparison of that monitoring data and the projected data. Now here, sort of similar to the graphics that Austin showed you, the horizontal lines that go straight back and forth across, those represent criteria or standards that we might be held to under permit. So you can see that red line is the strictest standard for arsenic. And the green line that you see The solid green line is the average concentration that's been measured in baseline. What that tells us is that based on conditions, as they're out there today and have been for the last several decades, are substantially higher than the strictest water quality criterion. That is, there's an arsenic concentration in East Fork, South Fork at this point that is well above the criterion. Now, if we look at the pink line, that pink sawtooth line, that is what the water quality would be at that point if we didn't bother to treat any water. If all the water that came down the hill, we would still use some of the water, right? But all the water that was excess water, if it didn't get treatment, we project that it would have water quality or arsenic concentrations represented by that pink line. And you can see that not only does it go above the solid green line, which is the average, it also goes above the dotted green line, which is the highest value ever measured at that point. So that obviously is not something we would want to see happen, right? So the treatment program that we came up with is projected to give us what we see in the sawtooth solid blue line. So that solid line shows you that zigzag pattern, which is really the effect of snow melt and dry times, right? There's actually more arsenic in the water when there's less water, and there's less arsenic concentration when the snow melts because you have a whole lot more water come down the hill and not a whole lot more arsenic. So what we see here is that even though there are a few times when you might have arsenic go a little bit above that green solid line, in other words, it would go a little above the average concentration today, that sawtooth blue line spends most of its time well below that concentration. And what that means is the water treatment, where we just treat the extra water that we can't use and put it into the stream, has a pretty noticeable improvement of overall water quality downstream of most of the Midas Gold operations. And that's what we're looking for. The next one, same story for antimony. I won't go through all the descriptions of the lines because they're the same, but suffice it to say that the pink line is not a situation we want to see where we end up with higher concentrations of antimony, but the blue line, the blue sawtooth line, spends much more of its time below today's average than above it. And so that means that on the balance, we're cleaning up water in East Fork, South Fork, Salmon River, because all of the water that touches Midas Gold facilities would get treated before it gets put into the stream. Okay, so just to summarize, I've said this several times, but we want to comply with the Clean Water Act. And the way we've done that is to come up with a water management plan and a water treatment plan that uses the best information we have available and uses standard engineering practices, so it's very defensible. We focus on making sure that we only discharge our mine impacted water if it meets our permit limits, and our permit limits are based on state of Idaho criteria. We are addressing the entire period from construction all the way through post-closure, no gaps in the schedule, and we're using a series of different proven treatment technologies, and through our bench testing and our pilot scale studies, we're only picking and using the ones that are the most suitable. And then finally, through adaptive management, we're making sure that we can adapt to any alternative that may be selected, and we're ready to respond to any changes either environmentally or with respect to new regulations or changes in the overall mine schedule that may happen after permits would be issued.
Well, I believe that's the last of our slides, Doug.
I think so.
Well, thank you guys. There's a few questions that we have in the hopper. The first one is, are the storage ponds and other ponds lined to prevent flow into the underground system?
The storage ponds, the contact water storage ponds are proposed to be lined, yes.
Wonderful. This, the second question is one maybe for Austin, and I believe you hit on it a little bit, but maybe it wouldn't hurt to hit on it some more. Why don't you think development rock will produce acid rock drainage?
Yeah, great question. That really has to do with the unique geology of the gold deposits of the Stibnite Mining District, and with the host rocks. So in summary, rocks in the West End deposit, there's a lot of carbonate units up there, metamorphosed limestones, which are now marbles and dolomites. And those rocks are really good at buffering acid due to the high carbonate content in those rocks. And then in the intrusive hosted systems, such as Yellow Pine and Hanger Flats, there's been a lot of potassic alteration, which has basically removed calcium from the feldspars in the minerals, in the mineralized areas, and redeposited this as calcite veining in the periphery of the gold mineralized areas. And this is the principal reason that the development rock outside of the gold mineralized zones has some potential for acid generation due to sulfides, but this is overall completely neutralized by the high carbonate content due to carbonate veining, calcite veining, and dolomite veining that we see.
Great, thank you, Austin. And then I'm going to throw this one at Dale, but please, anybody else, feel free to chime in as well. What would be the long-term water quality results of alternative 5, which is also known as the no action alternative?
I think that's probably best answered by Doug. Doug, do you want me to pull up one of the curves with the, well, I guess that's alternative 3.
Well, you know, I could start talking about this. You know, every day you look at things like metal loading, and there's something like 10 pounds of arsenic go down the stream every day and leave site, and this is largely the result of the you know, coming from the Meadow Creek disturbances, such as the Bradley tailings and the former mill and smelter up there. So I think that one result of the no action alternative would be basically to continue as is, with significant metal releases into the East Fork, South Fork.
If I could add one thing to that about something we had discussed earlier, I'm going to go back to one of Doug's figures here. Somebody had asked about, you know, soda. You know, in alternative 3 of the draft DIS, the tailings storage facility, as located here in the Meadow Creek drainage, alternative 3 places that tailings storage facility in the East Fork, Upper East Fork, South Fork, Salmon River drainage. You know, we'd seen on that one graph where the alternative 3 predicted constituents were higher concentrations, and Doug or Austin had mentioned that, or I believe it was Austin mentioned that is the result of this material being left in place in alternative 3. So one of the reasons we you know, alternative 3 is very definitely not our preferred alternative is that it does not remove, or it does not repurpose the soda, the spent ore disposal area, spent heap leach ore. It doesn't repurpose that as part of the TSF embankment, and it does not reprocess the Bradley tails. So that source does not get removed in alternative 3.
You know, something else just to tack onto that, it's kind of interesting. You might think that over time, these materials would leach out, and so you'd see a reduction. You know, like most of it came out during the 5 years after the previous mining company left, and then less the next year and less the next year. But it's fascinating. There were a couple of studies done by DEQ in the late 80s, and when you look at the arsenic concentrations that they were measuring down there at that YPSR4 near the bottom of the mine site, the concentrations of arsenic they were measuring in like 1987, 88, 89 are very, very close to what has been measured during a baseline monitoring in the last 5 years. So over a 30-year period, it's just as constant as it can be. So what that tells us is moving that stuff is way better than just waiting it out to see when it's going to stop leaching.
Perfect. Thank you, guys. Looks like we have one more question that I'm actually going to throw at you guys before we close up for the day. A lot of folks that are on this webinar are folks that are trying to get more information, are interested in the water quality and water management of our site, and are trying to garner some good, truthful information on what is going to be occurring so that they can comment during the public comment period. With that in mind, what are 2 or 3 things that would be best for them to take away when they go to start to write their comment?
This is Dale. I think one of the things we just spoke to, inaction is not the best option to my mind. I think we've demonstrated through thousands of samples and years and years of geochemical characterization and all the modeling we've done. Inaction will not result in improvement in this drainage. So inaction, i.e., alternative 5, certainly not our preferred action, but it just not doing anything, letting this run its course over time, it is certainly not the best option.
Yeah, I think I'd add to that due to the sort of extensive mineral endowment of the Stibnite mining district, which is what makes it a world-class mining district, and all the naturally occurring mineralization in the bedrock in that area, that even if we were treating all of the water in the area, we would still never be able to achieve water quality that is below the most stringent criteria, due to some of this naturally occurring mineralization and natural interactions of surface water with mineralized materials in the district. But we do think that under alternative 2 with treatment, we can get pretty darn close to making a substantial improvement in water quality leaving site.
And I would say a third thing to think about is that it's possible, if you don't know a lot about it and haven't read into it, it's possible just to think, well, so there have been several other mining companies that have mined up here, and we keep hearing about the legacy materials, and boy, it sure is a mess. And now another mining company wants to come in and just do more of it. But the real issue is that in the previous mining, for most of the mining history, there were not environmental regulations that were in place. And even in the more recent mining, there was not nearly the level of review by agencies and experts and other stakeholders. And there was not nearly the available engineering and science technology. So this is, by almost any measure, a state-of-the-art operation, from the concept to the planning to the engineering, the design, and then to the operations. So what that means is that what's going to happen from this point forward is an entirely different kind of thing than has happened up there before. And that's what gives the ability to do what Austin just said, and that is take something that didn't come out so well the last time and make sure that it comes out better this time.
Wonderful. Thank you guys very much. Unless Michael or Paul have anything to add, I'll go ahead and say thank you guys very much for attending the webinar today. Every Thursday, we do a deep dive into a part of our project. Next Thursday is financial assurance. I encourage all of you guys to sign up and send the registration link to family and friends. As you guys know, we are in the middle of our comment period. All comments are due by October 13th, and we greatly appreciate you guys sending in your letters of support and getting your family and friends to do so as well. If you have any questions regarding that, we are here to help you in any way we can. You can email me personally, Shelly or actually it's not Shelly, it's sbennett@midasgoldinc.com, or you can email our community email that is all over our website and our restorethesite.com website. So again, thank you guys very much. I hope you have a wonderful day, and we look forward to seeing you again next week.
Thank you, everybody.